Hello, my name's David Guildford. I'm a postdoctoral research fellow at the Centre for Hypersonics at the University of Queensland, and here I'm presenting a module on impulse facilities. Experimentation forms an essential part of studying hypersonics. There are a number of reasons why we conduct experiments. We need to test scientific hypotheses. We need to validate theoretical and numerical models. So that means to independently check our calculations and computer simulations. We need to generate empirical data because a lot of the time we don't know what the physical properties are until we actually measure them. And finally, we can also use experiments to demonstrate physical phenomena, so for teaching, including courses such as this one. In hypersonics, the wind tunnel is an essential tool to try and recreate flight inside the laboratory. When most people think of wind tunnels, they think of a facility which uses a large fan to blow air over a plane or an automobile or some other sort of model. In hypersonics, to go faster than this, we need a special type of wind tunnel, and that's called an impulse facility. In an impulse facility, we have a finite amount of test gas, and it is initially contained inside a tube. The test gas is first processed by a shock wave, which compressively heats it, raising its temperature and pressure. The shock wave also accelerates the test gas towards our test section. Then, depending on the facility, additional processes occur before the test gas flows over our model. Now, modern impulse facilities share some similar characteristics. They all achieve supersonic and hypersonic flows. The size of our model is limited by the diameter of the tube exit or the nozzle exit. Test times are short. We start with a finite length of tube filled with test gas and we blast it at hypersonic speeds over our model. Now this process only lasts a very short time. However, we can extend test time by using a longer facility. Hypersonic flow conditions are very harsh. Speeds and temperatures are very high for the models we are testing. Now to achieve longer test times, and to test larger models, we tend towards bigger and bigger facilities. The University of Queensland has a long history with impulse facilities and currently operates 4 of them. We have 2 types of facilities called reflected shock tunnels. So the large T4 facility and the much smaller Drummond Tunnel facility. These 2 facilities have test times of between 1 and 3 milliseconds. We can test models between 50 and 200 millimeters diameter, and we can generate test flows of between 2 and around 5 kilometers per second. Now to get to higher speeds, we use a type of facility called an expansion tube. UQ has 2 of these as well, the medium-sized X2 facility and the very large X3 facility. Test times are shorter with expansion tubes, between 50 and 1,000 microseconds. So that's 50 and 1,000 millionths of a second. Model sizes are similar, between 50 and 200 millimeters. But test flows are much faster, so between 3 and 15 kilometers per second. And we've even generated shock waves traveling at 18 kilometers per second in the past. So that's 65,000 kilometers an hour, which is fast enough to circle the globe in about 45 minutes. So in this module, we're going to look at both of these types of facilities separately. Reflected shock tunnels and then expansion tubes. Considering reflected shock tunnels, UQ has 2 of these, T4 and the Drummond Tunnel. Now, as we said before, these provide flows of up to 5 kilometers per second and test times up to about 3 milliseconds. The lower limits of these ranges are what the smaller Drummond Tunnel can achieve, and the upper limits can be achieved using the larger and higher performance T4 facility. UQ's smaller reflected shock tunnel is the Drummond Tunnel. This facility has a total length of about 6 meters. It can produce test flows with velocities up to about 2 kilometers per second and provide approximately 1 millisecond of test time. Now the Schlieren module of this course explains this facility in more detail. The T4 reflected shock tunnel is a much larger facility with a total length of about 50 meters. It fired its first shot in 1987 and its 10,000th shot in 2008. This facility was designed primarily for scramjet engine testing and could produce test flows up to about 5 kilometers per second for test times up to about 3 milliseconds. The T4 is higher performance than the Drummond Tunnel, Part of this comes down to the fact that it uses a device called a free piston driver, and now we'll talk about that in a moment. The other reason is sheer size. Now let's compare the size of the two facilities. So here we have T4, and in comparison, the Drummond Tunnel. So T4 is much longer, and that means there's more test gas, which gives us more test time. It is also much larger diameter, so we can test larger models. And finally, as we will see, it uses a free piston driver to shock process its test gas, and this permits much more powerful test flows. So in this slide we can see the general layout. So on the left is a large diameter tube called the driver tube. This is the engine for this facility, which energizes our test gas. In its initial position, a piston is held in place. Behind the piston is high pressure air pressing against the piston. And in front of the piston is a light gas such as helium, or a mixture of helium and argon. The front of the driver tube is sealed from the rest of the facility by a thick steel diaphragm. So that's this one here. The rest of the tube is narrower diameter, and one end of that tube is sealed by the thick steel diaphragm, which we've already highlighted. And the other end, near our test section, is closed off except for a small opening. So initially this small opening is sealed off with some thin plastic film, and we place our test gas, which is normally air, in the tube that's bounded by the steel diaphragm and the thin plastic film diaphragm. At the end of the small opening in the shock tube, we can see a nozzle. This nozzle is designed to expand flow, and it opens up to our test section where the model is located. So we're doing our experiments on this model here. Before the shot, the entire region from the small opening, so this point here, backwards, is pumped down and evacuated. This slide shows the initial configuration of T4 to produce a Mark 10 3 km per second scramjet test condition. So initially we have 12.5 megapascals of air. And this initially applies a force of around 40 tonnes on T4's 91 kilogram piston. Now in front of the piston is a mixture of helium and argon, initially at 1.5 atmospheres, so at a much lower pressure. Separating the driver tube from the shock tube is a sheet of 6mm thick steel plate. Now this won't rupture except at very high pressure. The shock tube contains the test gas. Now this tube in here contains our test gas, and what we're going to do is blast this gas over the model to simulate flight. Now the test gas is air, and it's initially at 2.5 atmospheres pressure. Now some thin mylar film, and mylar is a type of plastic, seals a small opening at the end of the tube. That's here, this small opening. And then the nozzle, as we said before, the nozzle, the test section and dump tank are initially pumped down just to a few hundred pascals, or less than 1% of atmospheric pressure. At the start of the experiment, the piston is released. We call the gas between the piston front face and the steel diaphragm the driver gas. That's this gas here. The gas in the shock tube is our test gas. And in these animations, we're going to pay attention to the movement of these zones of gas. The piston rapidly accelerates down the 25-metre driver tube due to the high pressure force applied to its rear face. As it travels down the tube, it compresses the helium-argon driver gas in front of it, simultaneously heating it. For most of the piston stroke, the pressure force behind the piston is much higher than the pressure force ahead of it. So the piston continues to accelerate and compressively heats the driver gas at the same time. However, eventually the pressure ahead of the piston rises to much higher levels than the pressure pushing it. Towards the end of the stroke, the pressure ahead of the piston rapidly ramps up, and the piston piles all of its kinetic energy into the driver gas. This process is called free piston compression. Around this time, the diaphragm, made of 6mm thick steel, eventually ruptures due to the enormous pressures. Around the time of diaphragm rupture, the driver gas has been compressed to about 75 megapascals, and the temperature of the gas is about 3,500 Kelvin. So that's that region in here. The high pressure driver gas expands into the much lower pressure air test gas after diaphragm rupture. This expansion process is extremely powerful for two reasons. The first reason is that the driver gas is at much higher pressure than the test gas. The second reason is that the driver gas has become extremely hot. Now, a hot gas has a high sound speed, and this is the key to the free piston driver. The hot, high-pressure driver gas can discharge its energy to the test gas extremely rapidly, and in doing so, it drives a very strong shock into the test gas. Now, we can see in the picture that the driver gas expands into the shock tube, driving the test gas towards the test section, which is why we call it the driver. Shock processing of the test gas compresses it and heats it and accelerates the gas towards the end of the tube. So we have compressive heating of this part of the gas here, which continues down that slug of test gas. So we can see that the test gas is compressed in length by the driver gas. And eventually the shock wave arrives at the end of the tube, which is essentially a closed-off tube except for that small opening to the nozzle. Now, behind the shock is high-pressure, high-temperature test gas, and it's moving at about 2 kilometers per second towards this dead end. The gas is stagnated by a reflected shock, which forms upon impact. The gas's kinetic energy is converted into even more pressure and heat. A region of gas forms at the end of the tube with a pressure of about 72 megapascals and a temperature of about 3800 Kelvin. Upon arrival of the shock, the thin mylar diaphragm is almost instantaneously obliterated, and this stagnated region of test gas expands through the nozzle. At this point, two things are now happening. Hot and high pressure test gas is expanding through the nozzle. This expansion process accelerates the gas and cools it as its pressure drops. At the same time, the reflected shock which formed at the end of the tube continues to stagnate the rest of the test gas further down the tube. A significant region of stagnated test gas is temporarily formed, which provides a supply of hot and high pressure test gas for expansion through the nozzle. This region here is termed the stagnation region or the nozzle supply region. This process continues. And it continues until the test gas arrives at the model. So at this point, the stagnated test gas has been expanded to the required scramjet flow condition, which in this case is a velocity of about 3 kilometers per second, a temperature of 217 Kelvin, a static pressure of 670 pascals, so less than 1% of atmospheric pressure, and all this corresponds to a Mach number of 10. As the test gas starts flowing over the model is now experiencing simulated flight, and our experiment begins. And again, this process continues. It continues until all of the air has been blasted past the model. At this point, the driver gas starts flowing past and the test is essentially over. So we can see the interface here between the two gases. Now, in reality, not all of the air test gas can be maintained at exactly the required flight conditions. So the useful test gas occurs a short time after the air starts flowing past the model and ends a short time before the driver gas arrives. So we use a period in between of steady flow to actually do our test. So we've just examined the operation of a reflected shock tunnel. Now we'll look into expansion tubes. UQ has two of these facilities, X2 and X3. As we'll see, these facilities largely operate in a similar fashion to the reflected shock tunnel, except we process the test gas a little bit differently. So here are the X2 and X3 expansion tubes. Observing the person standing next to X3, we can see that these facilities become truly large as we pursue long test times and want to test bigger models. Much of the expansion tube is similar to the reflected shock tube. We use a free piston driver to generate a strong shock in our test gas. However, in the expansion tube, the shock tube, this part here, is configured differently. Instead of being closed at its right-hand side, here, like on a reflected shock tunnel, our shock tube runs directly to our test section with the model placed at its exit. So we've got our model here. In an expansion tube, we want to divide our shock tube into different gases at different pressures. So we use thin mylar or foil diaphragms to partition the tube into different sections. So that's these diaphragms here and here. These diaphragms are just strong enough to resist any initial pressure differences in the tube. Here is the typical configuration of the X2 facility. Now, this configuration has been designed to achieve a Mach 10 scramjet flight condition. X2's driver operates in a similar fashion to T4's. Once more, it has a piston. It's a 10 kilogram piston, initially held in place. Behind the piston is 6.8 megapascals or 68 atmospheres of air pressure, and that's pushing the piston forward. In front of the piston is approximately 1 atmosphere of helium and argon. The large diameter driver tube is separated from the lower diameter shock tube by 2 mm steel plate. So that diaphragm is located at this station. Between the steel primary diaphragm and the mylar secondary diaphragm, we have helium gas. So we have our plastic film diaphragms at these locations. And in the first region, we have helium. The reason we've got helium in this section of the tube is to improve the test flow quality in terms of its steadiness. But this in itself is not important for the present discussion. Between the next two diaphragms, mylar diaphragms, we have about 7 atmospheres of air test gas, and that's in that region there. After the tertiary diaphragm, so we've got our primary, secondary, and tertiary diaphragm. After our tertiary diaphragm, the tube runs continuously to the test section and large dump tank. The model here is located just in front of the tube exit, and the entire volume downstream of that tertiary diaphragm is initially held at very low pressure. So in this case, about 288 pascals, or about 0.25% of atmosphere. Again, when we're operating this facility, the first thing we do is we release the piston. Now, pay close attention to what happens to our length of test gas. So, like with T4, when we release the piston, it accelerates down the tube, compressively heating the driver gas until the diaphragm ruptures. At this point in X2, the driver gas is at a pressure of approximately 240 atmospheres and a temperature of 2,800 Kelvin. First, the helium is shock processed. When the shock arrives at the secondary diaphragm, which is just mylar film, the shock almost instantaneously ruptures the diaphragm and then begins to shock process our test gas, which is the gas we're actually using in the experiment. Shock processing compresses and heats the test gas and accelerates it towards the test section. When this dense slug of high-speed test gas hits the tertiary mylar diaphragm, it ruptures it, and suddenly the test gas is exposed to practically a vacuum. At this point, the gas undergoes an unsteady expansion, accelerating towards the test section, a process which increases its enthalpy and total pressure. When the front of the expanded test gas arrives at the model, the test time begins. And when the last of the useful test gas passes the model, the test time ends. The unsteady expansion process involves a transfer of energy from the rear to the front of the test gas. Higher enthalpy and total pressure are achieved at the cost of reduced test time. Impulse facilities such as T4, X2, X3 and the Drummond Tunnel are required to produce flows for scramjet testing and flows for planetary entry studies. Each facility starts off with a finite volume of test gas and shock processes it. Where they differ is in how they process the test gas after shock processing, before the test gas is blasted into the test section. Which facility is used depends on the application, so all other things being equal. At speeds up to about 3 km per second, reflected shock tunnels provide the longest test times and the steadiest flows. If we need to go faster, we use an expansion tube. We'll now finish with a video showing the operation of the X2 and X3 expansion tubes, including the firing of the facilities.